Okay, so today we discuss laws of large numbers, and the law of large numbers is a statement that says that if you take a sequence of random variables which are independent and identically distributed with the expected value of xi, which is equal to mu, and this is finite, then the law of large numbers says that 1 over n sum over I from 1 to n of the xi, this is the arithmetic mean, or just the mean of the first n variables. And if you take n going to infinity, then this converges to the expected value. So the mean converges to the expected value. So this is a statement that is intuitive for many of us, but it's actually quite a non-trivial statement for several reasons. So first reason is that this object which is on this side is a random variable. It depends on the realization in a sample space, whereas this is just a number. Okay, this is just a real number. So what it tells, what the law of large numbers tells you is that in the limit when n goes to infinity, the randomness of the mean disappears, and you just get a number. Okay. So this is also referred to as a concentration property, because if you consider the probability distribution of this random variable, which is the arithmetic mean, then this probability distribution concentrates around one single value, which is the expected value. Okay. So, so it is a remarkable statement because essentially, so we have a lot of manifestations. So the first of these manifestations, this is the kind of statistical regularities that has been of interest for scientists for a long time, for more than 5 centuries at least. So, I mean, this idea that, say, for example, if you measure, if you take a measure of a physical system, then this measure can be affected by errors, and then in order to get rid of these errors, you should take this measure many, many times. And so the idea is that every time you take a measure, you will get a slightly different number, but and that there is a true number which is the actual value that this quantity that we are measuring takes. And so the idea is that when you take a particular measure of this physical quantity, there will be errors, but these errors somehow sometimes have positive deviations, sometimes have negative deviations. So if you take the average, then these errors average out. Okay. Now, this seems intuitive, but actually it's quite a non-trivial statement. So the fact that the deviations that we in each of the measures should average out. Okay, so there is another reason why this is a non-trivial statement, because it tells you that essentially whenever you want to compute a physical quantity, so if you want to compute the expected value of even a function of a given random variable x, then this actually would be the sum over all the possible outcomes of the probability of that outcomes times the function of x computed in omega. And so what these law of large numbers tells you is that we can estimate this expected value by just taking a large enough number of samples and just taking the arithmetic mean. Okay. So this is remarkable because if you look at this side, here you have a sum on all the elements of the sample space. And this can be a very, very large number. So, for example, if you think about a physical system, then this omega would correspond to a point in phase space. So, one omega would correspond to specifying all the positions and velocities of all the particles. So this sum is actually a sum on a very, very large number of terms, okay? And essentially, this is telling you that instead you can estimate this quantity by just taking the average over, say, a large number of values of xi drawn at random, but this n is much less than the number of points on which we sample here. That, say, for a physical system, this can be of the order of Avogadro's number, for example. Okay. So, so for example, in physics, we measure, for example, the say also the energy of a system by just taking we can measure by just taking a Monte Carlo simulation that generates configuration of the system and just computing the energy of that system over a number of states or configuration which are produced by our Monte Carlo algorithm. Okay, but by the way, notice also another thing that in physics, in thermodynamics, this is also the reason why the intensive quantities in thermodynamics do not fluctuate. So, so for example, you can think of the xi here being the energy of a system, or the contribution of energy. If you have a large system, then you can divide it into small systems, and you can measure a quantity like the energy in this particular small system. And then you can compute the energy density by summing over all these subsystems and taking 1 over n. So this tells you that, so the law of large numbers would tell you that if the law of large number holds, This will tell you that the energy density of a physical system is just a number, okay? Converges to a number. So it has a property that in physics it's often called self-averaging property. So by this one means that if you have a quantity such that if you describes a large system, then if you take the average of that quantity on a large system, that quantity does not fluctuate. It self-averages. Okay? Okay, so now if we want to discuss the law of large numbers, then we have to decide what type of limit we want to take here. And because as we have seen, there are different meanings that we can attach to this statement, to a limit in probability. And so there are two versions of the law of large numbers. And so the first version is what is called the weak law of large numbers. So the weak law of large numbers tells you is essentially this statement where convergence is convergence in probability. Okay, so if you want a complete statement of the weak law of large numbers, is that if you have a sequence of IID random variables with a finite expected value, then the weak law of large numbers holds if when you take the probability of 1 over n sum over I 1 to n of xi minus mu, and you ask whether what is the probability that this deviation is larger than epsilon for any given epsilon positive, then this probability goes to 0 as n goes to infinity. Okay, well now this limit is clear because we are talking about the limit of just a real sequence. Okay, so this is nothing but convergence in probability as we have discussed. Okay, so the weak law of large numbers would be just a statement, this statement here. Okay, so it has been proven that this statement holds whenever this condition is satisfied. Okay, you can get an easy proof of this statement. If the variance of the random variables xi are finite, then you can use Chebyshev inequality and show that the variance of 1 over n sum over I from 1 to n of the xi. So because the variance of the mean is equal to the variance of the random variable xi divided by n, and then you can use Chebyshev inequality here Chebyshev inequality would tell you that this would be less or equal than the variance of this object here divided by epsilon squared. But then, well, the variance of this is equal to the variance of this because mu is just a constant. And the variance of this is just the variance of the xi divided by n. So this is the variance of the xi divided by n times epsilon squared. And as we have argued, then when n goes to infinity, then this goes to 0. Okay. We will show when we discuss about limit theorems for sums that the law of large numbers holds for any essentially as long as the expected value is finite. But at the present stage, this will take a little bit more time. So, by the way, I mean, using the Chebyshev inequality tells you that the law of large numbers does not only hold for independent random variables, but it also holds for random variables which are weakly dependent, because well, you can see that the variance of the mean can be written as 1 over n times 1 over n squared times the sum over I and j expected value of xi minus mu, xj minus mu. Okay, so this is just, it takes just a little bit of algebra to show that the variance of this object can be written in this way. Now, if this is true, then you see that this is just the variance of the xi. Let's assume that the marginal distribution of the xi is all the same, divided by n, plus you have 2 times the sum over I less than j over n squared, the covariance of xi and xj. So this tells you that if the random variables are weakly dependent enough, so they are weakly dependent means that this covariance, so this sum grows slower than n squared, or that essentially this term goes to 0 as n goes to infinity, then you can use again Chebyshev inequality to show that the law of large number holds. So for example, one example where this is true is when you consider the xi, the sequence as being a time series. Then in that case, xi is the covariance of xi and xj. You can think that only depends on I minus j. Okay, so it's just a function of xi minus xj. And you can see that if this decays as xi minus xj to some power, then if this power is larger than 1, then this sum will behave as, so this sum in general will behave as n to the 1 so if this sum is, so if this exponent is less than 1, then what you can show is that this thing goes to 0 when n goes to infinity. Okay? Okay, so very good. Now, there is another way in which we can state the law of large numbers, which is the strong law of large numbers. And essentially, it deals with so the weak law of large numbers is this statement. The strong law of large numbers instead is a statement that 1 over n sum over I from 1 to n of the xi, the average, the mean, converges to the expected value almost surely. Okay? Okay, so what does it, so in essence, you see that the weak law of large numbers tells you that the limit of the probability of the deviations should be equal to 0. The strong law of large numbers tells you that the probability that the limit of the mean is equal to the expected value. So the probability of the limit, of this limit, is equal to 1. Okay? Or equivalently, that the probability of to have large deviations asymptotically is equal to 0. And so if you want a more precise statement of the law of large numbers, this is given by saying that however you choose epsilon delta small, you can always find an n of epsilon delta, which is an integer, such that the probability that 1 over n sum over I from 1 to n of the xi minus mu is less than epsilon for all n larger than n epsilon delta. Okay, so this probability is larger or equal to 1 minus delta. Okay, so you see that this is a very different statement because it is not a statement about one deviation, the probability of one deviation being exceeding epsilon, but it's a probability that for all n from a certain point on, the probability that there will be no deviation is close enough. It's close as much as you want to 1. Okay? So you can also write this, the law of large number by saying that if an is the probability of is the event to have a deviation of the mean larger than epsilon, then the the strong law of large numbers is equivalent to saying that the probability that these events AN occur infinitely often is equal to 0. So in this sense, you see the weak law of large numbers would tell you that the probability of these events AN go to 0 as n goes to infinity, and the strong law of large numbers that tells you that the probability that these events occur infinitely often is equal to 0. So it tells you that this deviation will occur only a finite number of times. Okay. Okay. So for example, we can show as an example a strong law of large numbers for the frequency. So how do we show the strong law of large numbers for a frequency? So here we take a Bernoulli trials. So the xi are IID and they are either equal to 1 with probability p or 0 with probability 1 minus p. And then we take Sn, which is just the sum from n from I from 1 to n of the xi. And so the strong law of large numbers would tell you that 1 over n times Sn converges almost surely to the expected value of the xi, which is equal to p. Okay? So how do we show this? Well, the way to show this is to consider this event AN. So in this case, the event AN would be the event that Sn over n minus p is larger than epsilon. Okay. And so now we can, what we want to estimate is what is the probability of AN. Okay. Now, we can estimate this probability if we remember that Sn is actually for n large by the Moivre Laplace limit. Sn can be well approximated by np plus the square root of n p times 1 minus p times a random variable z, which is Gaussian with mean 0, with expected value 0 and variance 1. Okay? And then this event AN is nothing but the event that this random variable z is, if you make the appropriate substitution here, this random variable z is larger than square root n divided by p times 1 minus p times epsilon. Okay. Now the probability of AN then can be computed by just, or can be estimated, because this is true for n larger, by just taking an integral of a Gaussian variable, estimate the probability of this event where z is a Gaussian value. Okay, so this is taking an integral from minus infinity to minus z and from z to plus infinity. But these two integrals are the same, so this is twice the integral from this lower limit, which is square root n p times 1 minus p times epsilon to plus infinity in dz over square root 2 pi e to the minus z squared over 2. Okay, and so we have already estimated once this integral when the lower limit of integration is very large. And we have shown that this asymptotically can be estimated as twice over square root 2 pi times the exponent computed in the lower limit, so the exponential computed in the lower limit, divided by the z in the lower limit. Okay, so this is e to the minus n epsilon squared divided by 2p 1 minus p divided by the square root of n p times 1 minus p. Okay? So you see that this probability, essentially apart from constants, but essentially goes to zero exponentially fast in n. Okay? So this means that the sum over n from 1 to infinity of the probability of an is finite. And then the Borel-Cantelli lemma ensures that if this is true, then the probability that an will occur infinitely often is equal to 0. Okay? So, okay, so very good. So let me take a short break here.